So, I did ask you all, right, to go home and provide the structure for C3H8O. Right? A little salt, maybe a little lemon. How many of you actually drew those? That's actually surprisingly good. Okay? That said, that was only maybe half the class. Okay? If I ask you to go through and do something like this, particularly if you see it attached to the word quiz, you should go home and do it, because typically what's going to happen in the first 5 minutes of class is I'm going to give you a little slip of paper, and I'm going to give it to you and say, write your name on it and write your answer. If you did it, you write your answer. If you didn't do it, you probably won't be able to solve it in the time I'm giving you to write that answer. Make sense? Okay, so be aware of that. So did anybody want to volunteer what they drew? C3H8O? If it makes you feel better, I will probably tell you are wrong. Okay. What do you got? Cool. So everybody can see it. Is that C3H8O? How many people got that answer? Like 2 people? Okay. I'm going to assume the rest of you are too shy to raise your hands. I guess only half the class did it. That is wrong. That is not what I was looking for. Anybody else come up with a different? I already talked to you. People who have already talked to me should not be asking.
I got these other 2.
You're being a jerk. What did you come up with? You're being a jerk too. Okay. So some people have already kind of pulled the trigger on this and said, well, what's going on here? Why are there different answers to this? Well, let's see what the other answers are. Does this structure satisfy that answer? It does. And how about this structure? Does that also satisfy the answer? Yes. Okay. So this becomes challenging because for that formula, you could get 3 different answers. Right? And talking to a few people, they were like, I got 8 different answers. And I'm like, you got 3 different answers at best and 5 copies of the answers you already wrote down. Okay. So let's take a look at that. Does this structure satisfy the answer?
Is that a double bond?
No. Where do you see a double bond?
The oxygen to the carbon. That looks like a double bond. To me, it does. 2 lines. Your H looks like an H. Oh, it's an H. Oxygen. Yeah. To get it all.
The one that goes with oxygen.
Like that?
Yeah.
It's not your bad. It's my bad. I drew it too close. Better? Okay. Does this satisfy the answer? It satisfies that formula. Is this different than what we already drew? Some people are like, no. And some people are awesome, jumped out there and said, yeah, it looks like it. Okay. So the test, and you'll hear this test happen a lot in this class. Okay, so let's run the test. What is my name? Mike, okay. What is my name now? It's still the same thing. Did I look the same? If I spent the whole class talking like this, are you going to have the same feeling when you leave the classroom? No, okay. So there's a different interaction there. You're seeing that from a different point of view. And yet, my name's still the same. It's because it's the exact same representation of the structure. Okay? The red structures are identical. There is no difference between them, okay, as far as their identity goes. However, our understanding of what they look like changes in our brain and makes us say, those are different things. They are not different things. Okay? And there's a couple big artifacts that mess with us on that. Okay? First and foremost, we've shown those all as solid lines, which makes it look like that carbon would be planar. Right? So bond angles are all 90 degrees. But you've all taken 151, and you know that a carbon with 4 groups of electrons is not planar because it is tetrahedral. Okay? And you're thinking, wow, I learned that? You probably forgot it because you never practiced it. That's okay. Okay? But you need to have that practice in there. So that's tetrahedral, which means all of those angles are 109.5. Okay? So that what we are drawing in those individual cases, good thing I don't have a red thing. How many carbons we have? 3? 3. This irritates me. I grabbed the wrong model kit. And because of that, my oxygen atom is going to be blue when it should be red. So first things first, there's our model kit, 3 carbons. What's the first thing you notice? It's not straight. Okay. It's straight now. Kinda. All those carbons are in the same plane, right?
Yeah.
Are all the bonds in the same plane? No. There's a 3-dimensional characteristic that is missing from our drawing here, right? But if we just say, okay, you know what, just for giggles, let's say that's roughly what it looks like. Stop spinning. They're all on a straight line. Well, when we go over to here, that's clearly not the case, right? Everybody see that? Okay. Did I break any bonds? Did I add new atoms? Did I remove atoms? Same structure. Okay. We are looking at it from a different point of view. And in that looking at it from a different point of view, our representation of it on the 2-dimensional plane will change. We have to acknowledge that we know what it looks like in 3 dimensions, and therefore those 2 red structures are the same. I've already talked about this with a few individuals. Women, unfortunately, have it bad with this because you weren't trained as a little girl to play with Legos, okay, or build things as a blanket kind of statement. Okay? I know we're generalizing, which means you haven't had that secondary practice. So if you're a guy, you're like, well, I didn't play with Legos either. Then you're equally screwed. Right? You need that practice to represent that 2-dimensional representation to the 3 dimensions and then back to the 2 dimensions so that you can constantly oscillate back and forth. Organic chemistry does that constantly. That is one of the biggest challenges with OChem, is to recognize that you're constantly going back from a 2-dimensional representation to the 3-dimensional to do something, then go back to 2 dimensions. We're going back to 2 dimensions so that we can tell people what we did. If you're in a multiple choice test, right? We do simple translations, right? In a multiple choice test, should we do the simple translation? No. What do we do on the multiple choice test? We go translation, cool, and then we go translation. And we do a rotation or a flip to the structure, because what does that immediately do to people taking the exam? Confuses them, and they now say, I can't solve the question. Ultimately, what happened is you didn't learn the very first thing in OChem, how to deal with those 3-dimensional rotations. That's why you're getting the question wrong, is for a very fundamental aspect in these first few weeks. Right? So, to that end, how do you fix it? Model kits. Right? Every time we draw something in class, have a model kit. Okay? Try and build it quickly, okay? And efficiently as possible. If it starts to drag behind, you're like, I'm not taking notes. The lectures are recorded. Go back and rewatch them. Rewatch them at home with the model kit so you don't feel like you're the only one playing in here. Okay? Class should feel like fun, believe it or not. Okay? It is fun. You can play. Okay? The part that you won't like is the exam. Play now so the exam is easy. Okay? So, formulas, horrible. We need to stop looking at formulas and we need to start thinking about structures. Okay? What becomes the problem with the structure? So we're going to simplify this a little bit. Let's just look at the red one. If I asked you to type that into a computer right now, how easy would that be? Not. Okay, good. It's horribly difficult to type into a computer a structure. Okay? You already had that physical issue with smart work. That's exactly what's happening here. Technology is improving. I have no doubt that the next step that we're going to look at is going to disappear probably within 20 years of chemistry, because our technology will have advanced far enough that we don't need to do this. We could just show the structure. Okay? So I want to represent that particular connectivity. I'm going to start with the core of organic chemistry being carbon. That's an eraser. Carbon. What is connected to that first carbon, which we will now call the red carbon? What's connected to it? For the red carbon, it's connected to 3 hydrogens. Okay? So I'm going to specify those 3 hydrogens. Okay? If I did that, and I now go from the formula to the structure, how many bonds would the carbon have? Only 3. How many bonds does carbon need to have? 4, because octet rule. Why do we know octet? Because you practice a ton of Lewis structure, which means there has to be something else out here. Okay? What's that something else? The blue carbon. What's connected to the blue carbon? 2 hydrogens. Would its octet be satisfied? Nope. So what's it connected to? The green carbon. What's it connected to? 2 hydrogens and oxygen. What's the oxygen connected to? A hydrogen. We're reading left to right to translate this, both directions, going from structure to formula and from formula to structure. What we're looking at is what's known, I don't know. Structural formula? I think that's it. It's called the structural formula. Okay? It gives us some information. The structure is by far better. Okay? Kind of makes sense? We had 3 structures to represent that one formula, right? Okay, and not the one I just drew, the C3H80. Yeah? Are those resonance structures? No. Okay? What was resonance? Okay, if we go up to our Lewis examples and we look at the hardcore rules, our resonance comes in when we satisfy octets by moving electrons. If we think about how we built those 3 structures, did we change where electrons were located, or did we change where atoms were located? We changed the location of an atom. Those aren't resonance structures. Resonance is only the change in location of electrons, not atoms. Okay? So what electrons are we allowed to work with? Okay? So if we take a look at, say, this structure, carbonate, admittedly I didn't show the charges, we could draw a bunch of resonance structures for it. Okay? And what I would argue is your practice back in Lewis should explain why you should have gotten this structure. Most people do this, they're like, well, carbon just needs to have 4 bonds, so I'm going to draw a double bond. That's not how we draw resonance. Resonance came about because when we follow the rules that I've established, we would get this for a Lewis structure. And what is the problem with this structure? Octet. That carbon is missing an octet. When do we do resonance? To satisfy an octet. By moving a pair of electrons. Which pair of electrons do I move? Any of them? So just this one I move? That would get me this structure. If you draw that for an answer for carbonate, you are wrong. I could have also moved this one in. And if I did that, what would my structure look like? That is different from the red box. Okay? And I could have also done this one. What I have now drawn is resonance, because what is the difference about those three structures. Which pair of electrons was moved? Did not change the location of the atoms. The atoms were pinned in place, but where I got the electrons to make that double bond is what generated my resonance structures. Okay? That's where resonance is ultimately coming from. If that's the base you have, now what we can do is add to that and be like, okay, let's simplify it. Because if I give you a huge structure to deal with, being able to go back to, well, why did I draw all those things where they were becomes very challenging, right? So organic chemistry now says, well, we start with this. How can I draw resonance? Okay. To get to this point, what did I have to do? I had to have electrons from the oxygen come down to the carbon. So if I want to change and now draw a resonance structure starting from this, the very first thing I need to do, move the electrons that are in that double bond back to the oxygen. Okay, so I'm going to show them going back to the oxygen. Shaking your head is nice, but if I'm looking at the ground while I'm writing this, that's very difficult for me to interpret. That's not correct. Okay, why is that not correct? It's not the right oxygen. Why is it not the right oxygen? Okay, we can encounter a lot of things for why that's not the right oxygen. Okay, one option being, people are laughing, that's good, but put words to it. We vastly exceeded the octet on that oxygen. Okay, what else is the problem? The top oxygen is now missing its octet. Okay, which brings up an idea on how electrons move. Okay, electrons are going to move very short distances. To go from this bond to that oxygen, that's a really long distance. I had to go through the bond, through the carbon, through that bond to get to that oxygen. That's a lot of motion. Electrons can't move that far. Yet. Okay? So let's go back and reevaluate that arrow that we drew. Okay? So in that statement, we said they moved to the oxygen. Okay? Well, there were tons of oxygens we could move to. Where's the most likely oxygen for them to move to? The top oxygen, right? Why? It's the closest to the electrons. Okay? Couldn't I have said the electrons in that pi bond go to the carbon? Isn't it equally close to that oxygen? So yes. Bev's saying no. Why are you saying no? So does the oxygen. Electronegativity. Which atom is more electronegative? Oxygen. Where are the electrons going to go? To the more electronegative atom. That's why they move that direction. If we tried to do the initial move where we jumped all the way to the other oxygen, we first had to move the electrons to carbon. Our very first step is taking the electrons away from the atom that wants them. That's a bad move. Okay? We can use electronegativity to help us predict where these things move. So, it moves upwards. What would the result be? That, okay? If we added formal charge, we would go like that, and we'd be like, what? I wouldn't be done yet because formal charge. There's too much formal charge in that. Okay? So since that is a bad structure, I can use that to think about my issues, but I don't want to show that as a resonance structure. Okay? Didn't I just show it? Yeah, so we'll fix that in a second. Too much formal charge, so what do I need to do? Get rid of the formal charge. Okay, I got rid of it. What do I do? Okay, I want to make a double bond. I want to move those electrons in towards that carbon. The resulting structure would look like yeah? Okay, I've got 3 structures drawn up here. I'm asking you to draw a resonance structure. 3 structures. You need to box correct resonance structures. Which of those 3 are you going to box?
The first one and the third one. But isn't there one more?
We'll deal with that in a second. Why do I not box the middle?
That's not.
Too many formal charges. I can use that to help me predict how things are going to move. That's awesome. I can't show that as a formal answer. If I now want to also add curved arrows to show how the electrons move, those curved arrows need to show up where?
On the original one?
Why on the original structure and not, say, the second one? Because the second one is not a valid resonance structure. It's okay to think about the work there. None of that work is allowed to count towards my answer. How can I ensure the work there also shows up in my black box?
Draw the other arrow.
Is that it? Yes. Okay. If this was on an exam, I'm fine with everything on this, particularly if you put the boxes on. You could also add an extra little layer here and you could do this. You are now telling me I know how to process through this, Mike, and I know that is a wrong answer, but it's my personal work and I don't want to erase it. Fine. I acknowledge all that. But you have specified how those things were supposed to move, what structures were resulted in, and how the electrons shifted around. Make sense? Okay, I heard a suggestion that there is a third one. Yes, there is a third one. What has to happen in the third one? The other oxygen has to share electrons in to make the double bond. What would happen if I did that, though? So let's just do that. Just like we did here. We've got work. What's the result? I'm not going to draw it all out. Carbon has exceeded its octet. That isn't an inherently bad thing, okay, as work. It is a horrible thing as an answer. Okay? So we could see that and go, the carbon has exceeded its octet, which means I would need to remove electrons. Which electrons could I remove? The bottom right one. Why do you want to remove the bottom right one? It's the only oxygen left. Thank you for giving me the answer I was feeding for. No, it's not. There's another oxygen right here. Why is that one not a valid move? What happens to the bond if that happened? That goes away. There is no bond. If there is no bond, is the oxygen connected to the carbon anymore? Have you changed the atom connectivity?
Yes.
Yes, not resonance. Okay? So that's why we can't target that top one. We can only target the bottom one. Those electrons could move there. Again, that's work. We don't want to show the work, so we can put a box through it. What do I have to add to my bottom structure? An arrow from there to there. The end result, I know I'm out of space. I apologize. ... Right? Good enough? Clear as mud? Some people are yes. Some people feel that hit too close to home, it looks like. Okay? So, I'm going to clear everything. Delete. Okay? So, which electrons were allowed to move? If we think about all the arrows that we used, what electrons did we move? We moved multiple bonds. We didn't touch it. When it was just a single bond, we didn't move that. The only electrons we could move were ones that were in a multiple bond. It is a horrible term, but we haven't addressed what a pi bond is yet. Maybe half the class knows what that is. The other half does not, so we can't use that. So multiple bonds. Multiple bonds can move. Okay? And non-bonding pairs. The lone pairs on the oxygen we're allowed to move. Those are the only two sources of electrons you're allowed to move. Okay? How do they move? If there's electrons in a bond, where do we move them to? To an atom. If the electrons were on an atom, we move them into a bond. Okay? The directions of where those electrons moved, they usually moved towards an atom that was more electronegative or an atom that needed an octet satisfied. That arrow shows the electrons moving where? The atom that was more electronegative. What does the blue one show? To a bond. Why is the blue one moving? To satisfy the octet. This is satisfying the octet? Okay. That satisfying the octet versus not becomes a challenging one. So I completely agree. It is satisfying the octet. So a lot of this is going to come from which arrow came first. Okay? You could go through and say, well, the blue arrow moved first, and then we had to fix the octet issue because we exceeded. Or you could draw the purple one and say, I've now screwed up my octet, now I'm fixing it. The exact order behind those isn't super critical as long as you understand why you're making those moves. Cool? Okay. If you were asked to draw the Lewis structure for this compound, okay, so this is going kind of Lewis structure realm and less resonance realm, but the resonance is going to pop up here. Okay? Notice the only electrons that are specified are in bonds. Okay, so this is a vague question. This is open-ended. This would be a Lewis question. What was step 1 of Lewis? Count the valence. So, nitrogen, how many valence? 5, how many nitrogens? Carbon, how many valence? 4. Hydrogen, how many? 6 total. Oh, -1, I forgot the charge, sorry. I usually throw charge in at the bottom. Because it's a +1, what did we have to do? We had to subtract 1 electron, so our total gets us to 24. Okay? So now we want to start placing our electrons in the structure. Electrons have already actually been placed for us. Why were they placed for us? If we just gave you the formula and said, draw the Lewis structure, we're going to get a lot of different answers. Those lot of different answers make it very difficult to grade because you could be correct, but then also horribly wrong. And so each individual is generating a different answer. That's virtually impossible to grade. So we gave you a skeleton form to say, this is where the atoms are, don't F with that. Place the rest of the electrons. How many electrons are already accounted for? 16. I got 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, no, it's okay. 18. So how many more do I need to place? Okay, got a couple people saying 6. I'm going to work with it. Where should we start placing those 6 electrons? I heard 1 on the carbon, okay, which is a super common place to place the electrons. It is also inherently flawed. Where do the electrons need to be placed? No. The electrons need to get placed on the most electronegative element. Okay? For those saying, well, nitrogen is the most electronegative. It is in this question. What happens if I change the question? Okay? So what you need to be thinking about is the long distance, not just one question, but propagate that out to an infinite amount of questions. So I'm going to start placing them on the nitrogen first. How much on each nitrogen? Why 2? We're going until we satisfy the octet. 2, 4, 6. Now what's our last rule? Anybody? What's that?
Carbon's on.
What'd you say?
Carbon
Okay.
formats.
Fine. You guys might be not jumping the gun. I was hoping someone would say formal charge. No, formal charge is not where we go. What do we do first? Satisfy octets. And in the process of satisfying octets, we will notice that carbon is missing its octet. So what do we need to do? We have to make a pi bond or a multi-bond by moving electrons from one of the nitrogens down to the carbon to make the double bond. Which nitrogen do we do? Any of them, which therefore means all of them. You have to draw 3 answers. Okay. Now that you've satisfied octets, now you can move on to the last question, which is formal charge. And when we go through and look at our formal charge, what are we going to end up with?
We don't have to specify the octet for hydrogen.
Okay. Hydrogens, it's not really an exception. Our octet has to do with the row that they're in, okay, and something to do about size. When we think about octet, Lewis built his theory primarily for boron, carbon, nitrogen, oxygen, and fluorine. Okay. What is special about that row? How many electrons fit into that energy level? I'm hearing a lot of 6. That is not the energy level. That would be the block. The energy level is the entire row. There are 8 columns in that row. There are 8 electrons in that energy level. Why did we achieve octet? Because almost all of the models that we looked at were looking at satisfying that row. Why did we want 8 electrons? So we can look like the noble gases. Okay? Is hydrogen in that row? No. Which row is hydrogen in? First row. How many electrons can I fit? 2, which means I can only fit 2 electrons there. Okay? So hydrogen doesn't get an octet per se. Some people will reference it as a duet rule, which I just think is kind of dumb. Okay? But it's valid. Okay? Hydrogen, only 2 electrons. Okay? All the other atoms have their octets. We could now go through and calculate formal charge. The nitrogen up here is positive, yeah? Cool. We now have an answer. Okay? Is that answer correct? 1 of 3. Okay, I'll accept that. As 1 of 3, is it correct? So if you went to the internet would say that was the answer for this. I forget who sent it, but no. The internet in this case said this was the correct answer. Okay. Unfortunately, the internet is wrong. Okay. The rules of Lewis structure say satisfy octets. Why is the internet going to this structure as an ideal form? Nitrogen's more electronegative than carbon, so they're trying to put the positive charge on the atom that is better able to stabilize it. That is okay. This is an awesome structure if I want to learn about its reactivity. If I'm looking at how to draw the structure, this is wrong. Kind of get it? So, again, I forgot who sent that. Thank you. Okay. If we looked at another structure here, okay, so we've got our rules written out, okay, stepwising through all of this. So let's take a look at this structure. Do I have lone pair electrons? No. Do I have multi-bonds? Yes. Sorry. Now I'm distracted. We have multiple bonds. Which multiple bond do you want to use? We'll call it left, top, bottom. Left. I want the bottom because somebody else said top. Does it matter? No, it's completely irrelevant. Okay? So I'm going to take those electrons and I want to move them somewhere. Those electrons are found in a bond. How am I allowed to move them? Wait, who's at the door? How am I allowed to move them? I can only move them to an atom. I have to move them to the proximal atom. What's the proximal atom? Carbon. So I'll move them that direction. What's the result?
You have to.
Oh, man. Did I touch any other part of the structure? No, which means it must all be drawn on there. I did not touch it. Leave it alone. Draw it back on there. I moved that pair of electrons where? To that carbon, which means that carbon now has a lone pair of electrons. Okay? This is the most common thing that we'll get. We'll be like, oh, it gained electrons, which means... Let's try it again. Carbon was neutral, no charge, and it gained electrons. Negative. So, good. We didn't make it... Well, it gained, so it must be positive. Gaining a negative becomes negative. There we go. There's the answer, and now I continue on. First giant red flag before you move on. The charge in your molecule, if you're doing resonance properly, will be the same in both structures. What's the charge in my red drawing? -1. What's the charge in the black one? 0. I screwed up the red one. What did I forget? It's a hint. We know it needs to be 0. I'm missing a positive. Okay? The positive is the most common charge to forget. How did that carbon become negative? It gained electrons. Where did it gain those electrons from? Well, it gained it from that bond. That bond had an electron from one carbon and an electron from the other carbon. The other carbon lost an electron, which means that other carbon is positively charged. Is this a good resonance structure? No, it's awful. Why? Charged. What do we need to do? Okay, so there's a suggestion for move other bonds. I'm going to say no. I'm going to say you should move the lone pair. Why should we move the lone pair? 2 people are running at you. The mountain and a 2-year-old. Who are you concerned about? The mountain. The mountain is more reactive, more dangerous. The 2-year-old is just like, dude, you're probably going to your mom? Like, what's going on? Okay. Which is more reactive, the lone pair or the pi bond? The lone pair, how do we know? It's charged. That's where my focus is going to be. So I'm going to move that lone pair. How do I move lone pairs? To a bond. What happens? What happens? I've exceeded the octet. I've drawn a horrible structure that I'm not allowed to draw. Okay? To fix that, if I've exceeded the octet, I need to break a multiple bond. Okay? How many multiple bonds do I have at this point? 2. So I could take the multiple bond I just made and move them. That's depressing. Backwards. Okay, in which case, that just undid what we did, right? So let's not look at that multiple bond. Okay, we could move it towards the carbon. Right? What's the problem with that? You just didn't fix the problem, right? You still exceeded the octet, which means we need to take the other multiple bond and move it where? Onto the carbon. Remember, this is an awful structure. I'm not allowed to show it. So I'll delete it here in a second, but I need to add this arrow. Where does that arrow need to get added? To the first one here. So that one's bad. I can't show that. What's the result? I hate showing hydrogens. We got a negative charge up there because it gained electrons. So now I can move on. Why not? I still have that positive charge. It's still hanging out down there. Is this structure any better than the red one? No, not really. So what do? Keep going. Okay? So I'm going to keep going as I do this. And you might be like, this is a bit silly. Where is this leading? Okay? Eventually, it's going to lead to this structure with all the bloomin' hydrogens again. Yeah? Is that any different than what I started with? We're getting no's and yeses. Okay, for those people saying yeses, why is it different? Was there a double bond on the right-hand side of the structure to start with? No. Okay, so it's different. Those are resonance contributors. Green and black are equivalent resonance contributors. If I asked you to draw the resonance for the black one, you draw the green one. Do you draw that one's red, and purple structures? No, why not? They suck because they have charge. So I don't want to show those. Those could be my work to process through to eventually get to the green, but I end up having to cross those out. Yeah? Kind of, sort of? Okay. Why are they not different? Well, it looks like you just turn the structure. Remember, resonance, you aren't allowed to turn the structure. The structure is pinned. Okay? The electrons in those multiple bonds are constantly oscillating around that entire ring. Okay? So they are resonance contributors. That helps to explain something about the reactivity of this. If I look at that pi bond, it is by far the most reactive thing. It's double bond, multi-bond, okay? Reactivity. Most reactive thing there. Okay? If I get rid of the ring, that multi-bond reacts pretty quickly. Okay? If I have the ring now attached to it, that multi-bond doesn't react. Why? For it to react, those electrons must come out of the structure. Where are those electrons spending their time? Are they in this bond? Or are they this bond? Or were they this one? They're all of them. Those electrons are constantly moving. If I'm going to run a reaction, right, you could apply it to boxing. You're in a boxing fight and you're trying to punch the other person. If they are constantly moving, that's going to be hard to punch them, right? Chemistry is doing the same thing. The more space your electrons have to move, the less likely they will react. So we've made them much more stable. The textbook talks about this or uses, they might have talked about the unicorn analogy, which I think is also equally dumb. Okay? That these two structures could be combined in one superstructure to represent everything about the reactivity of this compound, which is fantastic. We can call it a hybrid structure. And we go, oh, it's amazing. The electrons are constantly moving around there. So that's what that dotted line is showing. The electrons moving around, literally behind it. Okay? Neat. I want to make it react. To make it react, what do I have to grab? Where are the electrons? That makes it very difficult to show any reaction if the electrons are constantly moving. So if we're going to talk about chemistry and how things react, we're going to pick a frozen structure, not a hybrid structure. Okay? The hybrid structure is beautiful to look at. Cool. It's not useful. I can't ride a unicorn. A horse? Cool. There's the horse. Right? Make sense? Okay. So there's resonance. After all of this, what you're going to end up trying to come up with, or theoretically the conclusion from this, is you've got boron, carbon, nitrogen, oxygen, and halogens. Ultimately, the elements that we decided that we're going to work with in organic chemistry. You're going to draw Lewis structures with all of those compounds. You're going to know their valence electrons like the back of your hand. And the next part that should come out of Chapter 1 is that you will know their bonding patterns. Which means when I say carbon, you're 4 bonds. Okay? Doesn't mean 4 single bonds, but it's got to have 4 bonds. Okay? If I say chlorine, you know it has 1 and 3 lone pairs. That needs to be reflexive, so that when you're given the formula C3H8 H8O, you know roughly what all those pieces are, and you can jigsaw them a little bit better or smoother. Make sense? Okay. Are all of our structures going to be neutrally charged? No. So what else do you need to know? What happens if they're positively charged or negatively charged? I don't really care how you get that content stuck in your brain. It needs to be there. Okay? The best way is practice. Okay? After that, You have to have that content memorized, because if we have to draw out a structure and we get oxygen with 3 bonds and you're like, what's the formal charge? Let me calculate it. 6 minus 3 minus 2 is plus 1. It's a plus 1. If you memorize it, you see oxygen 3 plus. Done. Okay? Speed will matter. Okay? So then the next part. Shape of the molecule. Does that change the interaction? Yeah. My arm was coming out of my back, you would interact with me differently than if it's coming out of my side. Okay? So shape plays a really large role. So if we went through and looked at VSEPR, you looked at methane, you drew out methane, what does the bond angle look like? That bond angle when I draw methane looks tetrahedral. People are like, yeah, totally, that looks tetrahedral. That looks pretty dang flat. That looks like the bond angle there is what? 90. That's the problem with Lewis structure. Okay? For those people who are like, yeah, no, that looks not flat, 109.5. Interestingly enough, anybody listen to the tenor of the voice used to make that statement? It was all masculine. Okay? That shape is an inherent issue. And there's other factors behind that. But that shape is now bringing in that 3-dimensional characteristic. Okay? Be aware of those weaknesses so that you can fix it. So because Lewis failed, we came through and said we've got to do something to come up with it. That's where we get valence shell electron pair repulsion theory, and we get all the shapes, right? Name all the shapes. Linear, trigonal planar, tetrahedral. Trigonal, triangle, bipyramidal. Yeah, we start running into issues with these. There's a lot of different names for these. Tetrahedral is where we stop. Everything above tetrahedral, you need to know. Everything below tetrahedral, the bipyramidal, the octahedral, ignore it. I don't care. Okay? Are all electrons created equal? If I look at NH3 and draw out its Lewis structure, I still get 4 groups of electrons, right? Okay? But a lone pair is different than a bond. How? Okay? Here's a lone pair electron, right? I've got a lone pair electron in my hand, right? Would you say I own this or am I sharing this? Own it. What happened to the distance of the electron? It gets further away when it becomes shared. Much closer when it's owned. Which means the electrons are taking a different volume of shape, which means you get odd shapes coming out of it. You don't get a standard tetrahedral anymore because the groups of electrons are not the same. That's why we get those other shapes coming out. Okay? Bond angles, you're fine with 109, 120, and 180. I might ask a curveball question and say, do I expect the bond angle in trigonal pyramidal to be smaller or larger than in tetrahedral? Okay? For those people who memorize it, oh, it's just less. Explain. One of the things you'll learn in organic chemistry is how to cast magic in class. There's a tetrahedron. My wrist is that 4th group. If my wrist is now a lone pair of electrons, it's closer to the atom, right? So it pushes down. As it pushes down, it gets closer to these. So what do these, my fingers, do as bonds? They move away from it. What happened to the bond angle? It got smaller. What happens if I remove that lone pair? Those open up and make trigonal planar. So it's all about how the different electrons push against each other. Okay? Which can be done more prettily with balloons instead of your hand. Okay? There's a big summary that I usually throw out. That's all of it. You should know all of that. Okay? One of the things that I have not addressed yet, but we could layer on this. When are we done? 45. Cool. Hybridization. I didn't put hybridization on this. I wanted to throw it up there. Okay? And why not? We can test you guys. What is the hybridization for one electron group? That one's a bit of a... Yeah. There's no need to hybridize if there's just one group of electrons. Okay? What if we have two groups of electrons? SP. Three groups of electrons. Four groups. SP3. You can now work towards memorizing that. That's useful. We'll talk about why we get those hybridizations eventually. Okay? But we can add to that memorization. Okay? What does that 3 mean? It's SPPP. What does SP2 mean? SPP. Next one. SP. Last one. S. How many letters did I write? How many letters did I write? Yeah, that's usually what I said too. So there's an origin behind that helps to explain why that is the case. We'll look at that, or you may already have if you've watched that hybridization play pause it video, okay, which may have broken you too. I apologize. Okay, so VSEPR Applied. When we look at methane, okay, well, what is methane? CH3, close. CH3, shh, wait for me. Not always, it's fine to shout out, you're okay. CH3 is not methane, CH3 is methyl, okay, as a YL. What's the difference? Methane, we've ended the structure, it's done. Methyl is saying, I haven't ended the structure, there's more to it. Okay, methyl is a piece. Ane, or the NE part is saying I've ended it. Okay, so if I want methane, I need to end that structure. I just add one more hydrogen, I get methane. Okay? Does that best represent the three-dimensional structure for methane? Not very well. Why? Well, take a look at methane. There's methane. Does it look like all of those lines coming off that center knot are 90 degrees away from each other? No. Okay? There's a kind of default. Let's see if I can pull. I'm going to have to face the other way. Sorry. And we'll see this again and again and again. I have some problems with spatial reasoning. And you're like, you teach organic chemistry. And I'm like, I know. But I do stupid stuff like this to make sure I don't get it wrong. Okay? Bond, bond, right? Plane of the paper. Where's this carbon or that atom going? Coming towards you. If things come closer to you, what do they typically look like? Bigger. Whoops. So I'm going to show it as a wedge. I made those lines too thick. Everybody see that's a wedge? Yes. Does everybody agree with how I drew it? No. Why is it wrong? Here's the carbon. There's the hydrogen that ends this. Why is my drawing wrong? I'm only caring about that one wedged bond. That one wedged bond is currently wrong. If we look at where that wedge bond is, it is to the right of the carbon. Look at my drawing. I drew it where? Kind of to the left. Is that true? No. What does that mean? My drawing is wrong. For those of you being like, damn, that's nuanced and crazy, and I hope I don't have to do that. You don't technically have to do that if you get the answer right. You will likely have to do that to get the answer right. Okay? Your drawings need to as closely approximate the three-dimensional model as close as humanly possible. Art class. Where's this last one? It's going behind the plane. It's going away from you. If you're driving down the freeway, long stretch of road, because we get lots of those in Arizona, hot day, and you're looking out the stretch of the road, and you're like, whoa, there's sand drifting across the road, right? You've seen that? Looks like the road's kind of dotted. Then you drive up there, and you're like, there's no sand. Right? When it gets really far away, we get that kind of dotted effect. There it is. Yeah? We can now drop in the carbons and the hydrogens. Kind of, sort of? Yes. Is that the same thing? No. How do I orient this molecule to make this dashed bond up here? When I do so, what happened to that bond that was wedged? It's no longer wedged. What I just drew does not exist. It is not physically possible to draw. Okay? How can we ensure we do this appropriately? When you go through and draw your tetrahedral carbons, envision this as two V's. There's one V, there's the second V. The wedge and the dash are on one V, the solids are on one V. If at any point you don't have those two intersecting V's, you've done it wrong. Okay? Does it matter right now? No. Will it matter in chapter 5? Yes. Okay? So be aware of that. Cyclobutane, what do we think? Okay, bute. I haven't studied nomenclature yet. It sucks. Deal with it. Bute means 4. Okay? How do I know it goes in a ring-like structure? Kind of like a cyclo. Tells me that it must go into a cyclic structure. Okay? Each of those carbons has to have its full octet. Do they have their full octet? No. Because? Where are the hydrogens? So I have to specify the hydrogens. If I were to try and build this, what am I going to see? The hydrogens are all going to be staggered around. One up coming at me. One down going away. For those of you being like, I have no idea that that would be humanly possible, build the model kit. That's what it'll look like. Ish. Probably nicer. Okay? Chloromethane. What do you think? Do you see anything familiar in that name? Okay, interesting. Jumped all over chlorine. Okay. Saw chloro, which sounds like chlorine. For those of you that wonder about it, sometimes my chlorine looks like a U or an O. That's a C with a cursive L going into it, just for the record. Feel free to call me out on it. Okay? Where I was going is the familiar part, the methane that we literally just solved, right? Okay? So we could show this carbon, hydrogen, hydrogen. There's our chlorine. Where's our chlorine in this structure? Coming at you. Is that valid? No, there's no way you can get two bonds going away from you with the chlorine above the carbon aimed backwards away from the plane of the paper and two hydrogens aimed at you. Those of you being like, holy crap, he did just do it. Yes. Every possible permutation of that structure you have to be aware of. Okay? Is that a more difficult drawing to do? Someone like, no. You're telling me a wedge takes the exact same effort as a line. They're roughly the same. I didn't ask roughly the same. They're different. Okay? That drawing, this viewpoint tends to not get used very often. Okay? Because it is a lot more complex. There's a lot more pieces moving through it, a lot more different three-dimensionality with it. Okay? Just because it's not used often doesn't mean you don't need to know it. Okay? Methyl carbocation. What does that mean? Methyl, so carbon. We have the YL, which means we're just going to have a CH3. Whoops. So where do I put the wedge? For those of you that watched the Lewis play posit video and were really irritated at that third option, that was a loaded question. There is no wedge. That was a horribly drawn structure. With only 3 groups of electrons, the geometry is trigonal planar. The bond angle should be 120. Because it's planar, I can show all 3 atoms in the exact same plane, and I can drop the positive charge there. Yeah? Could I rotate that structure so that I could get wedges and dashes? Yeah, why not? Because I'm sick of 3-dimensional characteristics. Tough. What did I do to go from these 2 structures? Okay. First, technically what I did is I turned it a little bit, and then what did I do? Why would I do that? Mess with me, you're a jerk. Sort of. Partially valid. Who watched the hybridization video? Sorry, I might be throwing you under the bus here. What's the hybridization of that carbon? SP2. What's left over? What did not get hybridized? That's a hard question. Some people have gone through this a couple times, might be able to know that answer. Maybe you're holding off because you're nervous you're going to be wrong. Anybody want to volunteer? What's left over? I took an S, and I took 2 p orbitals to make that sp2, right? How many atomic orbitals does carbon have? 4. What did not get hybridized? A p orbital. Where's the p orbital? In this drawing, it has to be in a plane perpendicular to the bonds, which means where's the p orbital in this drawing? Coming in and out of the plane at you. Is that easy to draw? No. So what do? We tilt it. Now where's the p orbital? Now I can see the p orbital. For those of you saying my p orbital sucks, draw some yourself. Okay. There's our p orbital. We can now see it, and we can now predict something about how that structure can react. Yes?
Would you possibly say it would be like PZ that wasn't?
I won't ever get that specific as to which px, py, pz, because all of that is a frame of reference. So you would have to identify that frame of reference. It's not a physics class. I'll leave that to physicists. How are we doing? Yeah? What do we think? Easy? Straightforward? More confident? Maybe you can do half of chapter 1? Ouch. Okay, well. We're not going to do bromomethane because it's the same thing. So if I ask this question, draw the formula C5H12, what should you immediately be doing? You're drawing a bunch of lines. Okay, so a bunch of people are saying, I just draw out a bunch of lines. No idea what you're talking about. 12 hydrogens. And what am I going to say? Wrong. And not just because you abbreviated all the hydrogens. Why am I going to say wrong? Because what I wanted was, come on, give me my nice drawing. I wanted that one. For those of you being like, that's stupid. I know. That's why we don't use formulas. Okay? Don't draw formulas. Draw structural formulas. Draw Lewis structures. Okay? There are questions in the smart work that say provide all the structures for an individual formula. It sucks. It's to make you feel bad about formulas so that you stop using them. That's why it's there. So we've got a Lewis structure. Does that Lewis structure show our 3-dimensional shape very well? No. So what could we do? Redraw it by acknowledging our VSEPR model. Holy monkeys. That looks awful. Does it better represent the three-dimensional model? Yes. Okay? We could do line angle VSEPR, which is technically what I drew here. Okay? But I think I switched it up. What did I change? I removed the carbons. This is organic chemistry. Every time I have a point, I'm going to say it's a carbon. That was one of those organic simplifications. That simplifies my life. My drawing doesn't look awful or as awful. Okay? This is a bit obnoxious. I'm going to do it. How many carbons did I just draw? What are you talking about? One. That's a point. That counts as a carbon. Don't do that because it's impossible to see those. Okay? But what if I drew 2 carbons? How many hydrogens? 6. Each carbon needs its octet. Okay? Some people have that math down. Some people are like, oh, I got this. Slow your roll just a second. It does not hurt to spend the time to draw in those atoms. Okay? Make sure you're confident in your counting abilities. Okay? Line angle abbreviated. Everything disappeared. Everything can disappear because we imply it all. That formula or that structure has the same information stored in it in all the others, if not more. Okay? It is also much easier to manipulate, and we can work with that one. That's where we're going to be spending most of our life. We started with Lewis structure. We threw in VSEPR. Let's start making things simple. To get to this point, you have to know the implied hydrogens. You have to know carbon's supposed to have 4 bonds. Okay? For instance, how many hydrogens are connected to that carbon? 3. Good. 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 And maybe it's because the answer was already up there, but maybe you got it just because. You have to acknowledge the presence of those hydrogens. It is very easy to lose them. Make sense? Okay. So, simplifications, they're there. We need to find those patterns. Okay? So work towards memorizing those patterns. If you download the slides and you're like, I didn't see that, select the whole area. You'll see there's 2 white boxes covering that text. Delete the white boxes. Okay? And, why not? 3 minutes, let's see what we can do. Functionality, which might actually be chapter 2 in our new book, so I'm a little nervous on that. Everything wants to be neutral. Okay? That's pretty much everything we do in OChem is make it neutral. Okay? If we go through and look at this table, what are we looking at a table of? Electronegativity. Fluorine being very, very high means what does it do? It steals electrons, which means it becomes negatively charged. That's going to explain something about its reactivity. I need to neutralize that charge. Okay? So when we start putting atoms together with different electronegativities, that starts to give us some information, both about bond classifications and reactivities. Okay? So electronegativity is a big starting point for all of that. Okay? So what happens when we start connecting things? Ignore the sigma and pi for the moment. If I bond hydrogen to carbon, I have a type of bond. Right? What type of bond? Nonpolar covalent. That's going to generate a particular functional group. That functional group I'll call an alkyl. Not alkane, because I don't necessarily know yet, okay, what that ane ending means. If I have a hydrogen to a nitrogen, I'm going to call that an amine. Hydrogen to an oxygen, it's hydroxy. Okay? So I start identifying when I put these atoms next to each other what those bond names can be. Okay? When I start throwing in more bonds, okay, so if we look at these, we can kind of call this, actually we can get away with it here. We called these single, that says single, that also says single, and we called this double, that says double a little bit better. Okay? If I now have a carbon-carbon double bond, I have an alkene. Carbon-nitrogen double bond. I have an imine. Carbon-oxygen double bond. I have a carbonyl. So these are classes. What happens if I bring groups of these together? So if I had an OH, what did I have? Hydroxy. What if I had a carbon-oxygen double bond? A carbonyl. What happens if I now connect those two? Do I still have the chemistry of a hydroxy and the chemistry of a carbonyl? Turns out, no. Those two functional groups now affect each other. Because they affect each other, what happens? You change the name of the chemistry. Okay? You change the name of the functional group. Okay? What are all your functional groups? Several are combined. There we go. Functional groups to keep in mind. Okay, so I kind of got somewhat decent. That's not horrible. There's our functional groups. Your textbook has these. I'm going to real quickly go through and label these as first versus second semester. First/second. Oh, and I can put 2s next to everything else. Okay? Those are 2s. In the first semester, those are our primary focus for first semester when we're talking about their reactivities. I expect you to be able to name those. So if those functional groups show up, you should be able to say, that's an alcohol. That is actually not just an alcohol, that's butanol. Okay? Everything about naming those. The ones with 2s show up in second semester. That's when you should really be able to name those. In first semester, you should be able to identify all of them. You don't have to name them, but if you see a carbonyl next to an OH, carboxylic. You'll notice added next to it isn't just the nice structure, but I've also shown that formula, that structural formula, because sometimes the structural formula is not obvious. Okay? I apologize for talking too long.